Hello YouTube. Today I'd like to talk to you about calculus. And this explanation is going to be so simple that you could even show it to a grade school student. And yes, that is my intention. I would like this material to be used as an inspiration for homeschool parents that they can teach their own children far ahead of what they usually get in the public school system. So let's get right to it. I'm going to tell you what calculus is. The main idea of calculus is called a derivative. And a derivative changes one function into another function. And the word for this is an operator. So if we have the function x squared, it changes it into 2x. And the other important operator in calculus is called an integral. And we draw an integral with this symbol, and it does just the opposite. It changes it back. It changes 2x into x squared. So when we write this as an equation, we write d dx of x squared equals 2x. Or the other way around, we can write the integral of 2x dx is equal to x squared. Turns it back. Now, in many math books, you might see a x squared plus c written here. And the reason for that is that not only x squared, but x squared plus any constant will have the same derivative. If we have x squared plus 1 and take its derivative, that also becomes 2x. If we have x squared plus 2, that also becomes 2x. And the reason for this is that the derivative represents the rate of change. And no matter what kind of constant we add to the original function, it doesn't affect the derivative. Now I'll show you how a derivative can be used. And we use the example of x squared turning into 2x. Now the meaning of the derivative is to estimate how much the function changes with a small change of the input. So if we input 10 into x squared, the output is 100. And if we put 11 into x squared, the output is 121. So the effect of this function has been to increase the output by plus 21. And this is related to the derivative. If we take the original number, feed this into the derivative, 2x, the output is 20. And 20 is about the same difference as 21. That's an error of 5%. If we use a larger number, like 100, we get a more accurate estimation. 100 squared is 10,000. Now, as before, we increase the input by 1 to 101 and square it. This is 10,201. So the effect that we had on the output was to increase it by 201. If we take the original number, feed this into the derivative, 2x, we get 200. And 200 is about the same as 201. This time it's closer. Because 200 is a larger number, the error is only 0.5%. Make the number even bigger. If the original number is 1,000, the result of x squared is 1 million. If we increase this to 1001 and square it, now the result is 1,002,001. So the output of the function has increased by 2001. Now take the original number, put it into the derivative function, and we get 2,000, which is about the same as 2001. This time the error is only 0.05%. And a derivative also will give more accurate answers if we make a small change. So going back to the original example of 10, and this time we're only going to increase it by 1/10. And 10.1 squared gives 102.01. Now feed the original number into the derivative function, 2x, and we get 20. Now this time, before using the 20, we should multiply this times 1/10. 20 times 1/10 is 2. And now 2 is pretty close to the actual change in the output of the function. This was 2.01 and our estimate was 2. And here we have an error of 0.5%. So a derivative works better the smaller the change is. And that's what a derivative really is for. Now, let's work on some other functions. I told you that the derivative of x squared is 2x. The derivative of x cubed is 3x squared. So we can do the same sort of examples using these two functions. 3x squared is going to give us an estimation of how much the output of x cubed changes. The original number is 10, and cubing it gives 1,000. When the input is 11, cubing it gives 1,331. So we get an increase of 331. Now taking the original number 10, feeding this into the derivative, 3x squared, and the output is 300. And this is fairly close to 331. This time there's an error of 10%. And again, if we increase the number, we get a better estimation. 100 cubed gives 1,000,000. And 101 cubed gives 1,030,301. So the change in the output is plus 30,301. Now let's use the derivative to estimate the change. 100 fed into 3x squared gives 30,000. So 30,000 is approximately 30,301. And this time we have an error of about 10%. And as before, if we make a smaller change, we're going to get a better answer. We start with 10, cubing it gives 1,000. 10.1 cubed gives 1,030.301. When we take 10, feed it into the derivative, as we did up here, we get 300. But we have to multiply that 300 by the amount of change that we made. Naturally, if we make a smaller change, here we changed only 0.1, we're going to get a smaller change in the output. So it makes sense that this estimated change should be reduced by the amount that we reduced the change of the input. So we multiply 300 times 0.01 and we get 30. So 30 is approximately 30.301. Now, given those two examples, you've probably already guessed what the general rule for the derivative is. We'll look at a couple more examples and then show it. If we have x to the fourth power, the derivative is 4x cubed. And we'll go through the same example using these two functions. 10 input to x to the fourth power gives 10,000. 11 input to x to the fourth power gives 1,400 and 14,641, which is an increase of 4,641. Now we're going to use the derivative to estimate this increase. 10 fed into 4x cubed gives 4,000. And these are approximately the same. You'll notice that these estimates are getting worse and worse. But as before, if we make smaller changes, we're going to get better answers. And that's really how a derivative should be used. In the case of x to the fifth power, the derivative is 5x to the fourth power. So 10 fed into x to the fifth power is 100,000. And 11 fed into x to the fifth power, 11 to the fifth power, is 161,051. So the actual change is 61,051. And the estimated change using the derivative is 50,000. So significant error is creeping in here. But as before, smaller changes will give better answers. Now the general rule is that the derivative of x to the n power is equal to n times x to the n minus 1